This is a tutorial to guide you to work on your first project of the semester, heat capacity of material. There is a maple worksheet. What you need to do is to fill out all the answers in the worksheet and hand it in by the due date. There are two different heat capacities, Cp and Cv, because heat capacity is dependent on the process. The definition of Cp is change of the enthalpy per change of the temperature at constant volume. Cv definition is change of the internal energy per change of the temperature at constant volume. Enthalpy and internal energy are related as H equals U plus P V. Both enthalpy and internal energy has the units of joule. Both Cp and Cv has the units of joule per mole per Kelvin. Because of the definition of Cp and Cv, so Cp equals to change of the enthalpy per change of the temperature at constant pressure. Cv equals change of the internal energy per change of the temperature at constant volume. And so therefore we can find delta H equals to the integral from temperature T1 to final temperature. Number of the moles is N Cp dt. And change of the internal energy equals to change of the temperature T1 to final temperature N Cv dt. We can even find out the entropy change. Recall that the entropy definition equals dq reversible over T. And dq reversible is actually T and Cp dt. So therefore, if we want to find the entropy change between temperature T1 and T2, we can write down the integral as this one: initial temperature, final temperature, and Cp T dt. A very important concept is that Cp and Cv are temperature and material dependent. To appreciate that this concept, I encourage you to go to the webbook nist.government, and when you go to that website, it will show up here, and the thing you need to do is to click on this link, NIST Chemistry Webbook. So let me show you how you do it. So I open a new browser, and here I type webbook.nist.gov. Then I go and I come up with this website, and I click on the NIST web book. From there, you can type either the formula or the name, as I will explain in the next slide. So here is the web link that gives you to the NIST chemistry web book. And as I said that, you can either click on the formula or click on the name. And either way will bring you to the desired material you want to look up for the heat capacity. For example, I want to look up heat capacity of helium, and I click on the formula, and here I will type the HE that stands for the helium, and I will type gas phase. I will highlight the gas phase, and I will click on the search, and that will come out with the helium properties. And here I have all the thermochemistry data shown here. As I explained that to you, that I can also highlight the name, and here I can type the helium, stands for helium, and again I highlight the gas phase because the thermochemistry data depending on the phase. If the helium is a gas, so I will just kind of highlight the gas phase and search it, and I come out with all the gas phase thermochemistry data of the helium. On this web page, I look down the thermochemistry data. I see there are two links. One is to view the plot, and the other one is to view the table. So I'm going to highlight the view plot, and this gives me a plot of the helium heat capacity as a function of temperature. And you can see that one, the heat capacity of the helium is independent of the temperature, and the heat capacity value Cp is approximately equals to 20.79 joule per mole per Kelvin. Here's what I have copy and paste heat capacity of the helium into this slide, and the value of the Cp is independent of temperature, which is 20.79 joule per mole per Kelvin. If you follow the same procedure for the nitrogen, well, you get a very, very different characteristic of the nitrogen, and nitrogen heat capacity is actually dependent on the temperature. And starting from 29 something to all the way to about 38, and it is increasing with the temperature. The whole semester is to understand why the helium and nitrogen has a different temperature dependence of the heat capacity. To understand the difference between the helium and the nitrogen, helium is monoatomic. There's only one atom. Nitrogen is diatomic. Monoatomic has 3 moles of the motion, 3 moles of the motion, which is translation Vx, Vy, and Vg. For the diatomic, you not only have 3 moles of the motion or translation, you also have the 2 moles of the rotation. And 1 moles of vibration. Let's analyze this one even further. For the helium, I have 3 mode of motions. Each mode of motion contribute 1/2R. So I have 3 modes of motion multiplied by 3 equals 3/2R. And R equals its gas constant equals to 8.314. And this one will give me 12.47 joule per mole per Kelvin. This is the CV for the helium. And if for the ideal gas, Cp equals Cv plus R, so that will give me Cp equals to 20.79 joule per mole per Kelvin. Now let us look at the nitrogen. Nitrogen at the room temperature, the nitrogen has 3 moles of the translation plus 2 moles of the rotation, which is equals to 5/2R, and which is 5/2 times 8.314, and that equals to 20.79 joule per mole per Kelvin, and this is Cv. For the ideal gas, Cp equals Cv plus R, and that will give me 29.104 joule per mole per Kelvin. For nitrogen, as the temperature is increased, then that will kick up the vibrational mode, which will further contribute to the heat capacity. It is therefore this reason the heat capacity of the nitrogen increases with the temperature. The maple worksheet has a simple heat capacity calculation. This problem is actually I copy and paste from your Chem 1 exercise problem. And the problem states for an aluminum with 62.28 grams at temperature 98.69 degrees centigrade, drop into a cold water, and 82.68 grams of the water at 23.08 degrees centigrade. So as a result, the aluminum temperature is going to drop from 98.69 to finally the temperature 34.02, and the water temperature is going to increase from 23.08 to 34.02 degrees centigrade. The calorimeter is also increases from 23.08 degrees centigrade to 34.02 degree centigrade. Now we know the calorimeter heat capacity that equals to 1.89 joule per degree centigrade, and water, the specific heat capacity is 4.184 joule per gram per degree centigrade. Now, this problem is to ask you what is the specific heat capacity for the aluminum. To solve this problem, you've got to kind of mentally think the heat loss of aluminum equals heat gain by water and plus heat gain by the calorimeter. Heat loss of the aluminum is as S stands for the specific heat capacity of aluminum multiplied by the mass of the aluminum multiplied by the mass of the aluminum, which is 62.28 gram, multiplied by the temperature change, that is from 98.69 to 34.02. This is the heat loss of the aluminum. The heat gain of the water is 4.184 multiplied by the mass of the water, which is 82.68, and by the temperature gain is final temperature is 34.02 minus the initial temperature 23.08. This is the heat gain of water. Another one is the heat gain of the calorimeter, which has the heat capacity of 1.89 joule per degree centigrade, and the final temperature is 34.02 minus 23.08. These two plus together should be equals to the heat loss of aluminum. From there, you can find the S. The purpose of this exercise is for you to practice the maple worksheet, because this one you can do it from using the calculator, but as a matter of kind of practice with the maple, I think you need to gain some more experience with the maple. This is another worksheet problem that a calorimeter is heated up by 5.5 Kelvin by passing a current of 10 amperes, 12 volts, and for 3 300 seconds. And what is the heat capacity? One important concept is that the heat, the total joule, equals to the voltage multiplied by the ampere multiplied by the time. So you're going to equate the calorimeter heat capacity as multiplied by 5.5, that equals to the 10 ampere, 12 volt, and 300 seconds, and that will give you the joule. And so you will have the heat capacity or the calorimeter in terms of the units of joule per Kelvin. And again, this one you can do it with your calculator, but I kindly encourage you to practice with your Maple because you are beginning to learn how to use the Maple this semester.